Doing a video. Yes, doing one. Anyway, there's this thing somebody linked me to, which is kind of nice, you know, a little married couple doing their little, you know, whatever, videoing together and conversating and whatnot on gravitational waves. So I thought I would do a reply, sort of. So just get to the bits that I have something to say regarding, I suppose. I didn't really read through the comments, but they're probably stupid because, you know, everybody's stupid. Anyway, so they're talking about gravitational waves, and so they're talking about gravity and the bent space thing and the bent trampoline or something. Very British kind of accent here. But anyway, so there's this part. I think this is the part.
Fall towards the bowling ball. If you actually kind of throw a marble on at the right angle, it will kind of spin around.
Yeah, because you create a sort of funnel shape like that, so it's going to spin around.
Yeah.
Right. So, you know, I have been emphasizing the point that no, that's not what it's going to do. It will in your fake, you know, not real example of bent space, but in the real universe, no friction and energy in, energy out. Gravity is a conservational force, as they say, a conservative force, and so, yeah, nope, not going to work. It goes in, it pops back out, or it crashes into the thing in the middle, but you really don't do the orbiting thing unless you do something else. You have to have, you know, little reverse engines, or you have to have something to change the speed to get into an orbit. Interesting fact, I think. So, you know, it seems like a totally ignored fact, but, you know, I didn't know it until I thought about it. Science.
And that is a crude way of explaining what gravity actually is.
It's the warping of space-time.
The warping of space-time, brilliant.
It's really not very brilliant, you know, in my opinion. You know, it never made any sense to me personally. And you know, and then when you start thinking about it and just realize that it's just a way of visualizing this you know, relationship, this inverse squared thing, and that's all it's doing is duplicating this force effect. And you know, the fact that force gets stronger as you get closer. The fact that light bulbs get brighter as you walk closer to the light bulb, more light hits you. And so you analogize that to just bent space and say, okay, space is bent. But you can see how, no, every other force doesn't have anything. A light bulb isn't bent space. It's little photons flying out. More of them hit you when you're closer, and less of them hit you when you're further away. By the same relationship as gravity. And it just doesn't make any sense to say light bulbs are bending space. You see? It's all kind of silly. And, you know, Einstein was brilliant in the fact that he could get everybody to just say, yeah, okay, sure. Let's create a fake dimension called space-time, made of absolutely nothing, where the most energy in the universe, I mean, really it is an awful lot of energy. I mean, hurling planets into suns and stuff, I mean, that's a lot of energy. Yeah. So the biggest source of energy in the universe comes from a fake dimension. I don't know. Why does everybody fall for that? All right, play a little more.
So, by the way, I I really like that as a visual aid. It's very simple. What I don't like...
Yes. Oh, good. Get to the part where it doesn't fit the three-dimensional thing, where three-dimensionally it makes no sense at all, and the real world has 3 dimensions.
About it is, it's an explanation of gravity that requires gravity.
Yes, thank you. Yes, very good. Excellent. Bravo. Of the very point I have made. Kind of a silly explanation, really, when you think about it. Where does horse manure come from? Well, it's manure from a horse. Alright, that wasn't a very good metaphor, but you get it.
You know, you've got this rubber sheet, and you put a ball on it. The ball is pulled down by gravity, and the balls that you then put on it are pulled down by gravity.
Okay.
Right, and they're not actually pulled down in the right direction, right? Which is even worse, right? The gravity is coming down on top of them and pushing them down into the rubber, not pushing them down the slope, which would be the more rational. The energy is coming from even the wrong direction. So, and then the whole friction thing. I mean, it just doesn't work at all.
However, I mean, it's quite difficult to do an experiment to demonstrate gravity in a place with no gravity.
Yes, but that's not the point. Isn't to demonstrate it. The point is to model it, to explain it. Yes, that's really the point, I think. But anyway, particles. It's a photon. You see, it's invisible photons. That's what it's doing. Anyway, so I'll play some of this. I won't play the whole video. It's 25 minutes. See if we get to a part that's messy again. But yes, good save. Thank you. Alright, so, yeah, they did a little bit. He showed a video that I saw where a guy takes a graph and warps it to illustrate bent space, you know, on a baseball's trajectory and stuff. And, yeah, I was going to do a video on that just because, you know, I think it's inaccurate because, again, it's not calculating velocity, real velocity. It's just doing acceleration, and acceleration isn't terribly relevant in the sense that it's not your real actual trajectory. That'll be dictated by your velocity that you acquire from your acceleration. So as you're accelerating, your velocity keeps increasing, which gives you a different trajectory than just the increase in acceleration. But anyway, that's a whole nother point. It was just kind of funny they linked. I mean, it's a video I saw too, so it's kind of funny. Anyway, and then so he's getting on to. She was saying, okay, this gravity wave thing is two black holes colliding, and that's where she left off. You know, didn't say anything about the three solar masses, which is kind of tricky. And so he's saying about electrons and that they have a field, and they said another way to think about that is that they disturb a field. And this is the bit where they say something that, you know, once again I just say, doesn't this occur to anybody? Oops, come on, play.
The field moves as well.
Yeah.
The field doesn't move instantaneously, it moves at the speed of light.
What? Oh.
Yeah. So imagine I've got an electron here, and you're really far away, but you can feel the force of the electron, right? And then I move the electron over here, right?
Yeah.
And you can detect that the electron has moved.
Right.
I suppose the electron's moved away from you.
Yeah, he didn't, you know. I suppose you might be getting to the speed of light thing, but again, another giveaway. Gravity moves at the speed of light. I mean, it's just so. All these forces, magnetism, the electric flux, all of these things move at the speed of light. Come on. Isn't that saying something to you? They all kind of got to be maybe the same thing if they're all moving the same speed. Isn't that something you sort of realize in the real world? That like all the geese fly about the same speed, and you know all the fish swim about the same speed, and all the they all do the same thing. The same thing does the same thing. Photon, graviton, magneton, all the same kind of ton. Just a little tiny one has antennas, one doesn't. It's very similar.
Okay.
You can detect that it's moved away from you because the force got weaker, right?
Right.
But you don't detect it at the moment the electron moves. You detect it
the speed of light.
at the speed of light, so the time it takes for the change in the disturbance in the field to get to you.
Yeah.
Okay? So what happens if I take that electron now and I move it backwards and forwards like that?
Oh.
So that.
Yes, that. So yes, but again, let's realize gravity waves. We're talking about 30 solar masses moving the speed of half the speed of light. Matter, moving half the speed of light. First off, incalculably huge amount of energy. 30 solar masses moving half the speed of light. I mean, I can't, again, it's just incalculably huge amount of energy. Has to be dissipated somehow. Has to be dealt with. lots of imbalance. To using my rhetoric, lots of imbalance there to be balanced. Too much, I would say, yes.
That change in the field, that disturbance in the field, is kind of, it's, at this point here, it's getting bigger and smaller, bigger and smaller, bigger and smaller. Right? But that disturbance then travels through space at the speed of light. Okay. But here's the cool thing: when you disturb an electron, it doesn't just create a disturbance.
It'd be easier to understand by just saying that, as it's going back and forth, you just think that left is blue and right is red or something, and then it's more easy to visualize that they're just photons, and that red one, blue one, red one, blue one, and that the red blue ones have to travel across space, and they're still red and blue when they arrive at their destination. So
And the electric field that permeates the universe, it also causes disturbance in the magnetic field that permeates the universe. And that disturbance, those waves that travel away from it.
Well, again, it says that's just, what is that? There's a field, there's a magnetic and electric field that permeates the universe, and you're disturbing it with what? A photon? I mean, you can just make it simpler and just say, no, there's nothing. Which space looks like pretty much nothing, and photons are a something. They're not disturbing something, they're traveling through something. Come on. Why complicate it?
They travel in a packet of waves, and that packet is a photon.
Right.
A photon is a disturbance in the electric field and the magnetic field.
Well, again, it says you. All right. I don't think there's absolutely zero evidence that there's any electric or magnetic field except the ones created by things that are producing those fields. And those fields have every appearance of being created like a light bulb creates light. That they're creating a field of tons of some kind. All right. So that's all there is. The field doesn't go any further than what they've produced. As the light bulb only produces so much energy, it only, at an infinite distance, right? There's one photon per 7 bazillion miles.
Same time.
Yeah.
Right.
And they travel away from electrons when you jiggle them.
Well,
Okay.
it says you there again too, so I don't know about that one either. They travel away from electrons when you jiggle them. I mean, that sounds kind of, I think it'd be better to say is that when you shake anything in a crappy package, some of the stuff will fall out. I mean, if I take a box of cornflakes and I shake it, I can make cornflakes fly out. So yeah, electrons are made out of these little tons, and if you screw with them, tons will fly off. Sounds reasonable to me. Anyway, I'll be back. Alright, so he's sort of gotten onto the whole general relativity subject and the argument about what proves or disproves a theory, this whole idea of creating something that's disprovable, like this is some sort of rational concept. That you prove a theory by proving it's not disprovable or something. Doesn't make a whole lot of sense. I mean, all you're looking for is strong evidence, and you're looking for the absence of something that exists that you can't explain or is inconsistent with your theory. I mean, it's just basically any other trial. You're trying the evidence to say, is there enough to convict? Is there enough to say this is how it happened? This is the truth. And I suppose I would argue that the evidence for space-time is all weak evidence. He brought up the precession of Mercury as if Newton's diagram failed, and it didn't really fail, it just wasn't perfect, just as Darwin's description without genetics and a lot of other things was far from complete or perfect. And the fact that you could perfect Newton by recognizing not so much the precession of Mercury, we're talking really about the precession of the Sun. So that causes the precession of Mercury, the aberration in Mercury's orbit is really being created by an aberration in the center of gravity of the sun. Something Newton certainly had we shouldn't have any expectation he would be able to notice such things or know about such things. Newton didn't even know the sun was part of a galaxy, and so come on. But again, so the argument is that this Newton vision is in competition with this Einstein vision. Newton didn't even have a vision. He had no model. He had no explanation for the source of gravity. He just said this is what gravity does. And Einstein is just using what Newton figured out, adding a few nuance, very little, I mean 0.001% kind of nuance, and coming up with a source. But the source is suspect. It's this leprechaun of bent space-time, the non-existent dimension, the dimension that can't be found when you need it, when you want to test it. And it behaves in every respect like all the other forces that we know are not in some other dimension, that are in these dimensions, in the 3 dimensions we live in. That's where electricity and magnetism and all this stuff is. It's not in any other dimension. Anyway, so I think I got to most of that. And so I can just feel him now. He's going to list the proofs of general relativity, and so it's either going to be gravitational lensing, or maybe he's going to jump right to gravity waves. But I can feel it coming.
Disprove the theory of general relativity, and one of the predictions of Einstein's theory of general relativity is gravitational waves. So looking.
Okay, but so I mean that's sort of a fake context again, where Einstein was not too comfortable with he certainly didn't. The gravitational waves they're describing, where 3 solar masses are converted into gravitational waves, I don't think it has anything to do with Einstein. So I just think it's kind of a lie to say that's something to do with general relativity. It has to do with what people have done with his concept since his death, but I don't think it has anything to do with what he thought the concept was capable of. Just as I don't think he would think dark matter is a fair way to contrive the existence of legitimate evidence of gravitational lensing. Alright, so yeah, it all depends on what you call hard evidence and hard predictions. And really the key thing is one of these key points is that a fact has to be a necessary fact. To prove the theory, you have to kind of prove that it could only happen this way, that there is no alternative explanation. It's like at a trial, it's the capacity for there to be some other way it happened that makes evidence soft or hard. Okay, I mean the fact that people look a lot alike, or certain things, there's a lot of people that are 6 feet tall or something like that. And the fact that there's very few that are some kind of rare size 14 Bruno Mollies. That evidence that's how you weigh the evidence. If there were size 10 Bruno Mollies, it wouldn't mean anything, but size 14. Okay, and predicting things that can be explained by other mechanisms isn't necessarily is weak evidence. If it could have been any kind of 4-wheeled vehicle that left the tracks, you know what I mean? You can't say it's his 4-wheel vehicle. That kind of thing.
The gravitational waves is a really important thing to do in science, because you're probing. You're really figuring out, is this theory definitely true?
Right.
And the answer is never yes, but
it's okay.
It's
We've proven one more part of the theory.
Yeah.
It's
right. So it's one more part, depending on whether you accept the fact that this is enough information to say you found 2 black holes, 3 solar masses, gravity waves 1 billion light years away. And you somehow have an explanation for not only how the black holes got into this spiral, technically, how that's possible, what velocities they were coming in. So again, this is all very, I might argue, I don't think there is a rational model for this spiral. I don't think there's a rational way you can dissipate the velocity. And I certainly don't think you can make the argument that space-time can take matter from this dimension and convert it into space-time. That's not consistent, I don't think, with anything Einstein believed.
Even more likely to be true.
Yeah, exactly.
Okay.
So that's why we've been looking for gravitational waves, and that's why it's so important we found them.
Okay, so we found them. We did this. I don't know where that comes from. It's just so obnoxious. You had something to do with it, did you, fella? So again, it's really coming down to what like I said, Einstein's description of gravitational waves was merely the fact that two things spiraling around each other would be in alignment, out of alignment, in alignment, out of alignment. That's the gravitational waves Einstein was talking about. He wasn't talking about colliding black holes and then the release of 3 solar masses of energy creating waves. So I think this is all just so unfair to the argument to say we've proven general relativity by demonstrating something Einstein didn't even believe could exist. Come on. I mean, come on.
We still haven't got to what they are.
No, we haven't. So in Newton's theory of gravity,
again, Newton didn't have a theory of gravity. What Newton had was rock solid mathematical relationships that were only a tiniest of little minutia fractions off. I mean, we're talking about meters over billions of miles. Meters over billions of miles. That's how much error there was in Newton. And the error is just because he didn't account for, he couldn't see every variable. But he had no theory of gravity. He wanted a theory of gravity. He would have liked to say, this is what causes gravity. But he had no explanation for the cause. So this is just so unfair to say you're arguing Einstein's versus Newton. No, argue Einstein against something that was actually a theory of how gravity functions. But to say it's Newton math against Einstein math is just such a lie, because 90% or 95% of Einstein's math is Newton's math.
You feel the effects of gravity instantaneously, right?
Right.
So if the sun were to suddenly appear,
you don't feel the effects of gravity instantaneously. So where did you get that from? Yeah, I don't know where you got that from. I really don't know where you got that from. Where do you think you got that from? I mean, he just recognized the fact that it moves at the speed of light, and now he's saying we feel it instantaneously. Well, of course we do, because we're right on the Earth, and it's a very short distance. But obviously, the induction of gravity, it's a little different.
You would instantly be attracted to it, no matter how far away you are.
And yes, I know that that we now know that gravity travels at the speed of light, or the effects of gravity are felt at the speed of light.
Yeah. Well, this is one of the predictions of general relativity. So Einstein.
So I mean that was a. I mean, they do a lot of editing in this video. That's a part they should have just edited out, because that just didn't do much good. Yeah, I mean, to even play with the concept of what we feel doesn't really matter. The fact that you're going to be affected as soon as the wave hits you, gravity of any kind. I mean, if I'm a billion light years away from other gravity sources, and if they pull on a couple of my protons, just as a couple of photons from the space might hit my face, those photons are real photons. I'm going to react as if they happened right here and now, but clearly their source is a billion years ago. But my reaction will be real, and the photon is just as big and just as real as any photon in my real world. It's the same. It's just as real. So of course it's going to have a real effect on me. That's not going to have anything. There's not going to be obviously a fake photon, because it had to travel a billion light years. How far it travels is irrelevant to the force, but clearly we know the inverse square rule means that the force is going to be fairly weak over distance.
Einstein's theory of relativity.
Yeah.
Gravity isn't instantaneous. It travels at the speed of light.
Yeah.
All right. Well, I don't know why that's a theory of relativity again. So there's another. I mean, that was already something. Even in Newton's time, they speculated about, and they found out shortly after Newton, I think. So it was long before the theory of relativity that they established the fact that gravity probably propagates at the speed of light. You don't need there's nothing. You don't need bent space-time to do the speed of light of gravity. Come on, be fair.
So, in the same way as an electron is a disturbance in the electric field that permeates the universe, a massive object creates a disturbance in the gravitational field that permeates the universe.
Einstein's a genius.
Yeah, wrong. Yeah, Einstein's a genius. Again, creates a fake, a two-dimensional model that doesn't work in 3 dimensions, and in 2 dimensions it relies on the very force it's supposed to be explaining to work, and that's genius. I mean, it's a genius in the Barnum and Bailey kind of thing, right? You can fool all of the people all of the time, apparently.
Sorry.
I know.
It's just hitting me again. Maybe go on.
Okay.
Yeah, right. So you've just made a comparison between electrons in the fields they're functioning in and gravity in the fields they're functioning in. And we know the electrons are not being affected by the field. They're being affected by energy going in, photons, real things, not nothing, not space, not a vacuous field, but a field full of some sort of energy. Damn. Nobody thinks that field comes from nothing.
He's not. I mean, okay, Stu, not lowercase g, but so for example, do you know why he got his Nobel Prize?
No.
What field was it in?
I know that it's not what I would expect.
Yeah.
Well, what was it?
He got it for.
Well, whatever. Well, let me do it.
For quantum mechanics.
Oh, well, wrong. But whatever. Who cares? All right, so we'll move on. Yeah, it's not quite. I mean, to say it's quantum mechanics that he basically was arguing that photons are particles. Okay, corpuscles of energy, discrete and total, that they don't have halves or quarters or anything else, that they're quantum, complete particles, and they only function as complete particles, not as waves in reality. They only are detectable as complete things. Alright, anyway. Now this guy's getting a little annoying. I can feel the annoying. Alright, well, sort of really going off the whatever. Wiggle electrons, comparing wiggling electrons to wiggling black holes. Which, come on. And the two have never been associated. I don't think anybody's really making the argument that electrons are bending some sort of electron space-time, and that's the field being created by them and all. No, there's nothing comparable in these two things, so bad analogy in my opinion. He's called them electron waves, come on, it doesn't happen. A terrible description of the interferometer here, where he's talking about the light and using light just because it's supposed to be impervious to being distorted, and yet here we're supposed to believe it also can be bent by gravity. So how do you know if it's as subject to this material expansion as matter is, theoretically, because of lensing? So this seems a convenient. What do you call that? Can't have it both ways. If photons are just as subject as matter is to expansion and contraction in the presence of gravity, then your theory that your light is impervious to being affected by a gravitational wave is incorrect. So that part doesn't make much sense either. Alright, well anyway, he does a pretty poor description of. He talks about interference patterns and makes a comparison to the light creating an interference like that. It's so far out of phase that it's trough is meeting trough, or peak is meeting peak in a different wavelength, and all this kind of stuff. And the out of phase, the amount of this light is out of phase is a tiny amount of being out of phase that never even gets to being a half a wavelength out of phase. This is a tiny amount of being out of phase. This has nothing to do with interference and constructive and destructive interference. It never gets out of phase enough for any of the interference pattern nonsense to be any part of this. This has to do with a tiny phase difference between the two beams of light. So he doesn't even accurately describe that. So points off for that one, buddy. Alright, so we'll just play some of this, but it's just not a very good description of the hardware, and not a very good description of, again, not accounting for the 3 solar masses anywhere so far.
Right?
Yeah.
They're like, hey, presto, we've had a gravitational wave.
Yeah. Except that, because of like seismic things, you're like, if you've got a mirror that's miles away. I mean, this is LIGO, by the way. This is the name of the experiment. You've got, you'll have like seismic shifts, which mean that that distance is changing anyway. So you get loads and loads of noise. Okay. So you have to try and find this weak signal in loads of noise. And what they did was they built a LIGO at one side of the US and a LIGO at the other side of the US, where the noise is different, and they can somehow pick out the signal from the noise like that.
Well, obviously the noise is the same. It's the reason why it helps is because they can figure out noises that they hear in both. They can tell by direction of how long it takes for the noise to get to the different locations, whether it's a seismic, the ones they know of. But again, all that they can only clean the signal of noises they can anticipate. Noises that never have occurred, noises that might only happen every 1,000 years, they don't really have any capacity to filter for those. Really.
And that's what they did. And that's how they discovered the gravitational waves.
Okay,
so again, they did this, they did that, and I mean, this is just not very good evidence. Again, if this was a trial and somebody's life was on the line, this is a murder trial, and you're going to use this kind of, you're saying this is as good as DNA evidence? They discovered that there's a matching genetic code. Is that really what we have here? We have a result of a DNA code that matches gravitational waves. I mean, it's that solid evidence. I mean, what level of evidence are you going to call this? I say you have a smudgy fingerprint at best that has some vague similarities to what you might think gravitational waves might do to this giant hardware you've built. But you're a long way from DNA evidence. A long way. And not to concede that, it just makes this all so bogus. We've discovered, it's fact, it's a reality, no doubt about it. Again, this is as solid as we found a hair with a follicle. No. You haven't found hard evidence. You found vacuous, vapory. There's a blob on the video camera. Okay, yeah. So they just did some editing here, which was funny. I mean, they were doing tomato thing, and he made a joke that obviously dated her. Let's call the whole thing off from the song. Tomato. I mean, it was just kind of funny. But they cut that part out. So anyway, funny. And anyway, she's doing some kind of lame description now of what she's learned, so to speak, and it's really bad. So I figured I'll play it because, we can just enjoy the badness together.
LIGO were caused by the acceleration, and I thought the collision of two black holes.
Yeah, because the collision involves it. Like when they finally collide, they're just going so fast and producing such mad waves.
Oh, I see. So it's not like, so in my mind it was like they collide, there's this massive and then that sends like massive waves out across the space time.
It's not, no.
Okay.
Yeah. But
Yeah. I mean, their whole theory is that the wave going like this, okay, that's some energy is being released, and some matter is obviously having to be converted because they can detect it. So some of the solar masses are being released when the waves are far apart in the beginning. But when they get tighter together, they're saying that's higher energy, substantially higher energy. So they did a little picture of it in colors, and it's a big blob of energy right at the end. That's their little chirpy thing. It chirps, big splash of energy converted into space-time fabric, which again doesn't have anything to do with anything Einstein talked about.
Brilliantly, as they got closer, they spun faster and faster and faster. So the frequency of the waves they detected got faster and faster and faster until they
So that's
vanished.
what they're saying.
Yeah, well, the frequency gets faster, but the key point is the energy to create those waves. So the height of the wave is the amplitude of the wave. Yeah, never mind. Yeah, no, that really doesn't make any sense, right? Is it going slower at the same exact speed through this part, right? There's not any tightening at all, and then all of a sudden they go really quick. So it happens really quick that it all falls apart, whatever this falling apart is. So that doesn't work either.
And when they said they listened to these waves,
Yeah,
these black holes circling each other.
yeah. Where were we?
Oh dear, what a horrible thing to do, kids. Oh, she's gonna torture that poor thing. Anyway, where was I? I mean, that's alright. I mean, that's just terrible. Awful idea. Ugh. Crazy people. It's just gonna die. You sense it to die of something. Bravo. Live a nice, mediocre life, at the old grindstone. And of course, the future's gonna have to pay back all this debt and take care of all you people who didn't pay your bills. So they're gonna have to work twice as hard at the grindstone, and there's not going to be any jobs that are any good, right? So, and then you die. So really, thank you very much, assholes. I mean, you couldn't find something else to do with your time? Maybe you could do some better physics. You could look this stuff up and come up with better answers. No, I really dislike you. Anyway, where were we? Look, the whole idea is they're moving the speed of light. 60 solar masses moving half the speed of light. Just calculate the energy, please, somebody, and tell me how the hell you calm that down. How you dampen that into peacefulness again.
We were summing up.
Summing up.
Should we maybe explain?
This is Lyra.
This is Lyra. She woke up from her nap. So.
Oh God, Lyra. What the hell is that? Lyra. What? I named her after a liar. Oh, brilliant.
So she has come to help. Any object that is accelerating through space-time will create a gravitational wave.
Not any object.
Accelerating through space-time. I mean, no, it actually has to have mass, okay? So any object accelerate. No, it has to have what's called mass. A lot of it.
But acceleration is a requirement.
Okay, so what objects might not?
For
example,
a spherical object.
Yeah, minding its own business that doesn't have anything blocking it. So, something can be sitting, minding its own business, and the something else can just interfere in the sense that it goes in front of it and spins around it, and the wave is just blipping out or amplifying the signal, technically. Brighter. I mean, it's the opposite effect, right? Two things in a row means more mass in that line. See, I mean, if you understood this as particles, it'd be so obvious. Because it's kind of unintuitive, right? Light bulb and then shadowy thing in front of it. No, it's really, even when the light's not on, the light's on. So it's two light bulbs in front of each other.
So a spherical object is spinning, shall I say?
That is a mouth.
So imagine if you had a ball bobbing up and down in a pond, and you span the ball.
Mm-hmm.
If you did it just right,
Mm-hmm.
you wouldn't see waves coming off. But if you had a dumbbell and you span it in the pool, every time a dumbbell swept around,
it creates
it
waves.
would create a ripple.
Oh, yeah, well, it really is a horrible example. I mean, that just really doesn't have anything to do with it at all. I mean, that's just not a good example, right? Come on. That's not a good example. It's radiating. It's the waves aren't following behind. It's not cutting a path through, and then the waves radiate out. It's creating real speed of light stuff that instantaneously leaves. It doesn't hang around for a while and then leave.
Yeah, okay.
This
That would
is
work on my tarpaulin, in my rubber sheet analogy as
it,
well.
it would.
Which I still think is really rather good.
Yeah, okay, fine. So, well, let's go with that. So, if you span a heavy ball on your rubber sheet, you wouldn't get waves. But if you span a dumbbell on the rubber sheet, there's actually 3 clouds. 1, 2, 3. If you span a dumbbell on the sheet, you would get ripples out. Okay.
Right, but again, this has little or nothing to do with what they're saying happened, which is these 2 items, as they spun, destroyed 3 solar masses and converted them into gravity waves. 3 solar masses not released as photons or matter or something else, but released as bent space. So, come on, let's get the story right.
Yeah,
I like the way that I can visualise that. That
Good.
works for me. So most objects accelerating through space, time, apart from spherical objects, for example.
And cylindrical objects.
So, almost all objects, as they accelerate through space-time, will create gravitational waves.
Yeah.
Yeah, well, they won't. We're accelerating right now into the Earth, and we're not waving at all. But whatever. Yeah, I'll come back for the finish, or the wrap-up, or whatever. Ugh, annoying. Yeah, I mean, that just wasn't great, and then that just was, oh, fuck. Depressing. Ugh, horrible ending. Oh, just a mush, kid stuff. Anyway, so Einstein's equations, the universe is a solution to them, some sort of mush like that. And no concession that most of Einstein's equations are just Newton's equations or somebody else's equations, just piled in together. Just already things that are known relationships. Known relationships between things like mass and velocity and acceleration and distance and time. All things we know of as things, real things. So there's no bent space factors or anything like that. The equations are made out of real things, and it's just trying to account for a very complex system. You have a lot of moving parts, and so there's a lot to account for, so the equation gets kind of big. It's like if I had to make an equation for somebody's car parking at the shopping center, the equation would get preposterously large in terms of analyzing all the friction and all the heat and all the energy and all the ways it's used. It would get kind of complex. And yes, the universe is much simpler than a car, but the point is that interactions are always complicated between things, and they have lots and lots and lots and lots and lots of little parts. There's not too many varieties, just 100 elemental table kind of thing, but they do different things. Some are magnetic, and some do this, and some do that. And you have to figure all that into the equation somewhere about how much of it's going to hit an electron, how much of it's going to hit a proton, how much of it's going to go through the empty space, and how much it's going to do this, and how much, and it's all a bunch of percentages, and it's all kind of gets very complicated to figure out how it's going to happen over a period of time. But there's no magic in there, and most of it is equations other people already wrote. Shit. All of it, really. But anyway, I mean, look, I'm a big fan of Newton, but Newton got most of his shit from the other guys, you know, especially the guy with the planet orbit thing, whatever his name was. You know, so he got a big piece of the puzzle, and even Galileo had already done a hunk of it. So, yeah, but whatever. This concept is just wrong, and it's too bad that everybody's lost in this babble. Real universe is made out of energy, and there's energy in the matter, and there's energy in the space, and it's all just little tons moving the speed of light. And some of them you can see, and some of them you can't. But you can see what they do, which is this. And they just pushed that pen down. Anyway, so they gave the pen acceleration. The pen absorbed the ones going this way, and it didn't absorb the same number going the other way, so it went this way. I mean, it's just so simple. It's unfortunate that this is, you know, this is really as simple. Don't have kids because they're going to die, and they might not like it here. I mean, there is evidence, you know, that mostly reasonable people are injected into this game and find it pukable. I mean, I happen to be one of those people who, you know, have never been too pleased with my presence here among you. And so, yes, okay, play the odds, you know, do your little gambling thing. But if you lose, you'll just cop out. You'll just say, well, too bad. Tough shit. You know, I can't shove you back. Fuck you. For what? So you can play little silly games. Be distracted. Plaything, that's all. It's just a plaything. Ugh, disgusting. So anyway. Yeah, that'll be enough. So until next time and such. Mold. Steve Mold. So her name is Lyra Mold. Something like that. Lyrie, whatever the fuck it was. Lyrie Mold. Lying Mold. Not a very good chick name. Anyway. But I guess it's better than little Horsey Horsalot. Probably better than that. So, till next time.